Last time we were together, we talked about dipole-dipole interactions. Those are the intermolecular forces that are stronger typically than the London dispersion forces that we worry about in nonpolar molecules. We're going to look at an even stronger type of intermolecular force today. But before we get there, I want to look at this graph. In the graph, we see several boiling points of compounds plotted against the row that they are in on the periodic table, also known as the period. We're going to look at each line, but we're going to start with the one that is purple, the one that has the lowest boiling points. This isn't necessarily a surprise if you start looking at these molecules like CH4, which has the lowest boiling point. It's a molecule that has tetrahedral geometry, and because it's tetrahedral, it is a very symmetrical molecule and therefore nonpolar. That means CH4 only has London dispersion forces, and London dispersion forces are pretty easy to break, which makes having a low boiling point make sense. The other members of the purple line actually have the same shape. So if I drew any other member, for instance, if I draw now SNH4, it's also going to be a tetrahedral molecule that only has London dispersion forces and therefore still has a pretty low boiling point. But it's higher than the one that we see for CH4. Why do these two molecules that are shaped the same exact way, why do they have different boiling points? Well, remember, London dispersion forces depend on the total number of electrons or the molar mass of the compound. SNH4 is much heavier than CH4, so it makes sense that it would have a higher boiling point than CH4. But they're all still low because they only have London dispersion forces. Let's go up a group or two. If we look at the blue line now, for instance, I'm going to start by focusing on HCl. If you look at HCl, HCl is a polar molecule. It has to be polar because you only have two atoms, and those two atoms are not the same. So HCl would have dipole-dipole forces in addition to London dispersion forces, because truthfully, all molecules have London dispersion forces. It turns out the dipole-dipole forces are strong, and so it has a relatively high boiling point. But look at other group members. For instance, HI. HI, just like the same argument we made before, is the same exact shape as HCl. It's also polar. It also has dipole-dipole forces. But HI has a higher boiling point than HCl. Why? Because its London dispersion forces are stronger, has more electrons, it has a greater molar mass. We could do this with all of the groups. If I looked at H2S, for instance, H2S is a bent molecule. H2S is polar. Any molecule that has lone pairs on the central atom is going to be polar. So it has dipole-dipole forces and a relatively high boiling point. H2TE, which is in the exact same group, has a much higher boiling point. Again, same reasoning as before. While it's polar and also has dipole-dipole forces, it's heavier than H2S, has more total electrons, and therefore it has stronger London dispersion forces, harder to break apart, and so it has a higher boiling point. So what's interesting about this graph then? I think really the interesting part comes from three molecules that just feel out of place: NH3, HF, and H2O. They're both the lightest member of their group, and yet they all three have the highest boiling points in their group. And that doesn't seem to make sense. Let's focus on water, for instance. If I look at water, water is also bent, just like H2S and H2TE. So it's polar, it has dipole-dipole forces, and it has London dispersion forces. In fact, its London dispersion forces are weaker than H2S and weaker than H2TE. So if I were to if I thought about it, H2O should have a boiling point that was more like somewhere around here. It should be around negative 75 degrees Celsius. But thankfully, it's not. It's 100 degrees Celsius. So it is really about 175 degrees Celsius higher boiling point than you might expect it to be. And we could do the same thing with HF and with NH3. That means that for those three molecules, there's something else going on. There's something else that's allowing those molecules to stick together better than we thought they should. And that something else is what's known as a hydrogen bond. I'm going to be honest, I really don't like the use of the word bond. This is an intermolecular force, just like dipole-dipole and just like LDF. In fact, it's really just a subset of dipole-dipole. The hydrogen bond, while not a real bond, not a covalent bond or an ionic bond or a metallic bond, the hydrogen bond is the strongest of all of the intermolecular forces. Now, if you look at the picture, the hydrogen bond happens between molecules, just like all intermolecular forces, as we see right there, or as I see right here. So what makes it any different than the other forces that we've talked about? Well, it's the special nature of hydrogen when in particular it's bonded to one of three atoms. So what are those atoms and why are those atoms special? Well, it turns out to form hydrogen bonds, you need a couple of things. You need one of these three atoms bonded directly to hydrogen, nitrogen, oxygen, and fluorine. These three atoms have between them the highest electronegativities on the periodic table. That means they're really good at pulling away electrons from themselves or to themselves and away from another atom. So they really pull the electron away from hydrogen. So we need first a hydrogen atom to be covalently bonded. Okay. This is not the hydrogen bond. This is a covalent bond. It's sometimes referred to as an intramolecular force, okay, within the molecule. This is a real chemical bond. And we need to make sure that hydrogen is covalently bonded to NO or F. And so we see that in HF. If I were to look at this molecule right here, we would say that that covalent bond is a bond between hydrogen and oxygen. So that is number one on the list. You have to have hydrogen atoms bonded to a very electronegative atom, NO or F. In addition, the intermolecular force that we are calling the hydrogen bond needs to be between a hydrogen atom in one molecule and a very electronegative atom in another molecule. Again, NO and F are the only three atoms that really capture this. Okay, so let's look at the right side of the screen and look at HF in particular. If I look at HF, HF has the covalent bond right here. Okay, this is what we call the hydrogen bond. It is just an intermolecular force that holds those molecules to one another. It just happens to be that it's particularly strong. Again, if I look at water on the left-hand side, the H bond is the area of attraction between the two water molecules. We just need to look out for NO and F. And when we do that, we see some dramatic properties. Take a look at these two molecules. We've got ethane on the bottom, and we've got something called methanol on the top. Now, if you look at methanol, methanol has one hydrogen that is capable of making a hydrogen bond. Okay. We wouldn't say that it is a hydrogen bond. We would say that it's capable of making a hydrogen bond. Okay. It's this hydrogen right there. Why? Because it's directly bonded to an oxygen. It's directly bonded to one of those three atoms that we said was necessary to make hydrogen bonds. But if I look down here at ethane, ethane doesn't have any hydrogens capable of making a hydrogen bond. Again, why? Because none of those hydrogens are bonded directly to O, N, or F. So I've got these two molecules. They're roughly the same molar mass. That means that their London dispersion forces should be about the same. And yet, we see that you can boil ethane at negative 88 degrees Celsius. That's a relatively low boiling point. It means that it's pretty easy to break the London dispersion forces that we see in ethane. But in our molecule methanol, methanol has a boiling point that's not only positive, it's very positive, 64.7 degrees Celsius. That's suggesting that there are really strong forces holding methanol molecules to one another. And those forces, again, are hydrogen bonds. Again, we don't say that the bond itself between here, the oxygen atom, and the hydrogen, that's not the H bond. That's a covalent bond. That's an intramolecular force. What we're caring about mostly here is this area of attraction between the two molecules, between the H and the O on the other molecule. That is what's referred to as an H bond, and that is very strong. Now imagine you have millions and billions and trillions of molecules doing that. You have a substance that is linked together in a very strong way. Of course, it's going to have a high boiling point. Okay, that's it for hydrogen bonding. We'll see you next time.